Hello, everybody. I hope you've had a good couple of days off. Hopefully, you've been working on your series packet, at least doing the assignments from last week. If you have not yet read my email, please do that. It has some important information just about the expectations and the different assignments for while we're out of school, as well as just some updates on the teacher walkout from my point of view. I just want to encourage you, please, now is not the time of year to stop doing homework or to give up. This is a time when we really need to buckle down, work hard, and really push through. We're just about a month and a half out from the AP test. So all your hard work will be paying off soon, but please, 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 even while we're out of school, you have got to take this class and your other AP classes very seriously. So I'm just going to start by going over the homework from Friday, and then I'm going to make a separate video that's going to have some notes on an additional assignment. So first is page 3. You're going to be writing the sequences from above, first in sigma notation, then telling whether the series converges or diverges. So for number 1, in sigma notation, we would have the sum from n equals 1 to infinity of 2 plus n cubed over 2 minus n cubed. And if you, I'm sorry, that is out of focus. Let me see if I can try to lock that in. Okay. So if you can look above, we saw above, let's see if I can do that this sequence converges to -1. And remember, the nth term test for series, which you should do every single time, says that a series cannot converge unless its terms go to 0. And a little bit more about why that has to be true. If you think about series convergence, for a series and infinite sum to converge, that means that sum has to approach a number. And if the terms don't go to 0, then that infinite sum would have to go off to infinity. Think about adding 1 plus 1 plus 1 plus 1 forever. That sum would go to infinity. It wouldn't converge to a number. The only way you can converge to the number is if you're adding numbers that are getting closer and closer to 0. And so because the terms in this are going to go towards -1, this automatically diverges. It fails the nth term test. Okay, and actually, all of these 5 are going to diverge, except possibly number 3, because all of those fail the nth term test. So like the next one, we have the sum of, let's see, 3 times 3 over 2 to the n. The first term is supposed to be 9 over 2. So we go from n equals 1 to infinity. That's a geometric series with r greater than 1, therefore it diverges. Also fails the nth term test. This is geometric, r is greater than 1. The next one, the sum from n equals 1 to infinity of 2n over n factorial. So this one does not fail the nth term test. All the terms go to 0. So if we want to figure out whether or not this converges, we need to pick one of our other tests. And anytime you see a factorial, we want to try the ratio test. So that's where you compare a sub n plus 1 over a sub n. And you see that that limit as n goes to infinity has to equal something less than 1. Okay, so I'm going to do the limit as n goes to infinity of the absolute value of a sub n plus 1, so that'd be 2 times n plus 1 over n plus 1 factorial, divided by a sub n, so 2n over n factorial. And as in absolute values, this limit has to equal something less than 1 in order for it to converge. So let's try to evaluate. So I'm going to go ahead and rewrite the n plus 1 factorial as n plus 1 times n factorial. Flip and multiply by the denominator. So these n factorials cancel out. The n plus 1s cancel out. And then the 2's can cancel out. So I end up getting the limit as n goes to infinity of 1 over n, which equals 0. Okay, therefore, since that's less than 1, this series converges by the ratio test. So it took up kind of a lot of space there, but that's okay. And then number 4 is the sum from n equals 1 to infinity of the cosine of pi over n squared plus 2. Well, we said that the sequence converges to 3, because as n goes to infinity, cosine of 0 is 1, and 1 plus 2 is 3. So this fails the nth term test. So it diverges, it fails the nth term test. Okay, and then the last one will be the sum from n equals 1 to infinity of n over sine n. Well, this one is going to go, this fails the nth term test. The actual sequence goes to infinity. Therefore, the series for sure goes to infinity. So this diverges. It fails the nth term test. Okay. So that is page 3. Let's move along now to page 5. So on page 5, let's focus that up. We should have already completed the top 6 problems from Thursday. There's kind of the answers there for you guys. So now we're getting to the rest of the test, starting with alternating series tests. So this, to me, was going to be the best way to go over homework questions, because we just need to continue moving along, and I know it's really hard to email questions with all these symbols and all that kind of stuff. I thought about doing like a Facebook Live or something, but then I'm like, well, these people aren't on Facebook, blah, blah, blah. So anyways, I just decided the most important thing is that you learn the material, not necessarily that I'm such a stickler on this homework. So we're all just going to kind of work through it together. Okay, so alternating series test. There are 2 conditions that must be met. The next term has to be smaller than the term previous. And then all the terms have to go to 0. So first thing you're going to do when you do the alternating series test is just pull out the part that's not the alternating part. So in this case, the a sub n will be 1 over n. So we're kind of ignoring the negative 1 to the n, that part. And so then the question is the limit as n goes to infinity of 1 over n equal to 0? Because it has to. And yes, it does. So it meets that criteria. The other one is that the terms have to be positive and decrease. So you can just kind of look at a couple terms. The first term, a sub 1, will be 1. A sub 2 will be a half. A sub 3 will be a third. And yes, each term is smaller than the term that came before it, and they're all positive. So it meets that criteria also. Therefore, this one converges. Converges. Okay. Let's look at the next one. So remember, pull out the part that's not alternating. So like the square root of n over n plus 2. Okay, so let's take the limit as n goes to infinity of a sub n. So just use Bobo-Botten, right? So now we're not even regarding the sum right now. We're just doing the alternating series test. So the limit of this sequence here is 0 because it's bigger on bottom. N to the first, that's bigger than n to the 1/2. Can you hear my daughter singing? She's pretending with her Barbies. Anyways, okay. So the next condition is that the terms have to decrease and be positive. So let's find our first term here. Square root of 1 over 1 plus 3, so that'd be 1/3. Our second term, square root of 2 over 4, which actually is bigger than 1/3. Interesting. So it's looking like maybe it doesn't meet that criteria. But when I find the third term, square root of 3 over 5, that's smaller again. So sometimes it's not enough to just check the first two terms. They may increase for a little bit at first, but as long as after a certain point, they're all decreasing after that, then it still meets the criteria. So this one's a little bit bigger, but then this is smaller again. And if you find the fourth term, so square root of 4 over 4 plus 2, so over 6. Sorry, it's super messy, which is 2 over 6, or 1/3. We're back to 1/3. Let me see really quick what that square root of 3 over 5 would be. So 3 square root of 3 over 5. Yeah, it's like 0.346. And then square root of 2 over 4 is like 0.354. Okay, so notice from 1/3, it does jump and get bigger on the second term, but then after that, it's steadily decreasing. Goes down to 0.34, goes on to 1/3, which we know is about 0.33, and it will continue to decrease after that. So long-winded way of saying, yes, it passes that second condition as well. So this series converges. Okay, so that's kind of a tricky one. Okay, the last one, the sum from n equals 1 to infinity of -1 to the n times 3 over n squared. Sorry, I didn't mean to do that. So we're going to look at our a sub n, which is the part that doesn't alternate, so 3 over n squared, which is a p-series. Okay, so this is a p-series with p equal to 2, but that's not actually what we're doing here. We are doing the alternating series test, which means I have to show that the limit as n goes to infinity of a sub n is 0, which it is, and I have to show that the terms are getting smaller. So the first term will be 3 over 1, second term 3 over 4, third term 3 over 9, etc. So those terms are definitely decreasing. Okay, so it meets both criteria, therefore it converges. Okay. Next. All right, so now we have this page of series convergence to look at. So first we're starting off with the integral test, which is a great review of chapter 8, which was on our improper integrals. So the integral test says that if f is continuous, positive, and decreasing, and f is the function related to this series, and the function is positive, then it converges if the integral converges, it diverges if the integral diverges. So we just set up, sorry, got blurry on us. Let me get my page ready. Okay, so we just set up our integral. Okay, let's check the two conditions. The first one is that f, so our f of x would equal 3 over x plus 1. Okay. And for this one, we have to prove that this function is positive and decreasing. So this is positive for x greater than 1, which is all we're concerned about because that's where n starts. So check, yes, it's positive. Is it decreasing? Check, right? So the terms as x gets bigger. Goodness, this focus drives me crazy. So as x gets bigger, the terms get smaller, right? These fractions, the denominator gets bigger, so the fractions get smaller, which means we can use the integral test. So I'm going to integrate from 1 to infinity, or I'm just going to go 1 to b and do the limit as b goes to infinity. All right, that's how we do improper integrals. Of 3 over x plus 1 dx. So the integral of that would be 3 natural log absolute value x plus 1 from 1 to b. Don't forget, I'm doing the limit as b goes to infinity of all that. So that equals the limit b goes to infinity of, so I have 3 natural log b plus 1 minus 3 natural log 2. So what happens as b goes to infinity? Well, if b gets bigger, this natural log will get bigger forever and ever. So this is going to go off to infinity. Therefore, the integral diverges and the series diverges. So it diverges. Not going to work. All right, let's try the next one, e to the negative n. So first we have to show that it's positive and decreasing. So remember, e to the negative n, that's the same thing as 1 over e to the n. That's definitely going to be positive all the time. It's positive and decreasing. Yes, decreasing as well. As n gets bigger, or x, the terms will get smaller. So that means I can do the integral now of e to the negative x dx. I just change it to an x when I do an integral, just kind of to be proper, because I'm integrating a continuous function. I'm not integrating a series, because those are discrete terms, separate terms that are not continuous. So I'm integrating the related function to this series. And I'm going from 1 to infinity. Instead of the infinity, though, I'm going to put a b and write the limit as b goes to infinity. Okay, so when I integrate, I still have the limit as b goes to infinity. But then I have negative e to the negative x, right? From 1 to b. So I have the limit as b goes to infinity of negative e to the negative b minus negative, so plus e to the negative 1. Okay. So let's think about that limit there. So that's the same thing as negative 1 over e to the b. So sometimes with the negative exponent it can be confusing. So I just rewrite it as a fraction to help myself figure out what in the world is going on. Okay, now it's easy to tell that when b goes to infinity, this fraction is going to 0, right? So I'm going to be left only with 1 over e. And the rule is if the integral converges, which it does because it equals something, then the series converges. So this one converges. Now, does the series converge to 1 over e? My answer is no, not necessarily. So it doesn't mean it converges to the same thing. Like the integral converges to 1 over e. Does the series converge to 1 over e? I'm honestly not sure. But the conclusion that we're making is just that it converges, not necessarily what it converges to. Okay, so that's integral test. Let's look at the ratio test now. So I like the ratio test because to me it's pretty straightforward. We're just going to do the limit as n goes to infinity of a sub n plus 1 over a sub n, the absolute value of that. Then if we get something less than 1, it converges. If we get something greater than 1, it diverges. Pretty simple. So I'm going to do the limit as n goes to infinity of the absolute value of a sub n plus 1, so 2 to the n plus 1 over n plus 1 squared, divided by a sub n, so 2 to the n over n squared. So it's the limit as n goes to infinity, absolute value. So I'm going to rewrite that as 2 to the n times 2. That's the same thing as 2 to the n plus 1. And then over that n plus 1 squared, you can leave it like that, or I think I'm going to write it as n squared plus 2n plus 1. I'll just FOIL it out. Then I'm going to flip and multiply by the bottom. So n squared over 2 to the n. I'm encroaching on the area of the next problem. Whoops. Okay, so the 2 to the n's cancel. Nothing else does, but we can still figure this out. So the limit as n goes to infinity of 2n squared over n squared plus 2n plus 1. I can use Bobo-Botten to solve that limit, and I just get 2. And the rule is with the ratio test, if it equals something less than 1, then it converges. Greater than 1, it diverges. So this one diverges. Okay, next one. This is alternating, and it's something sort of complicated. So that's why we're going to use the ratio test here. So I'm going to look at the limit as n goes to infinity of a sub n plus 1. So negative 1 to the n plus 1 times 2 to the n plus 1 over n plus 1 factorial divided by a sub n, so negative 1 to the n, 2 to the n over n factorial. Flip and multiply. And I'm going to kind of rewrite this. Negative 1 to the n times negative 1 times 2 to the n times 2. So I'm just separating these n plus 1 exponents because it makes it easier to cancel things out. So divided by n plus 1 times n factorial times, I'm going to flip the bottom right here and multiply. So I have the n factorial on top, and the negative 1 to the n and the 2 to the n on the bottom. Okay? Cancel, cancel, cancel. So negative 1 to the n cancels, the 2 to the n cancels, the n factorial cancels. What am I left with? The limit as n goes to infinity of negative 2 over n plus 1, which as n goes to infinity, Bobo-Botten, bigger on bottom, that goes to 0. And the rule is if it goes to something less than 1, the absolute value of this, goes to something less than 1, then this converges. So this one converges. Yay. Okay. Last one with the nth term test over here. So we're going to look the limit as n goes to infinity, the absolute value of a sub n plus 1. So n plus 1 factorial divided by n plus 1 times 3 to the n plus 1 divided by a sub n. I'm actually just going to go ahead and flip and multiply. So times n times 3 to the n over n factorial. So I just went ahead and instead of dividing by this, I flipped it and I multiplied. Okay. I'm going to rewrite some of this stuff so it's easier to cancel. So I have n plus 1 times n factorial over n plus 1 times 3 to the n times 3 times n times 3 to the n over n factorial. Okay, what cancels? The n plus 1, the n factorial, the 3 to the n. And I'm left with the limit as n goes to infinity of n over 3, the absolute value of that. Wow, well that's going to go off to infinity. So this one diverges. Let me put a little line here. Okay. Ratio test done. Now I have direct comparison and limit comparison. So our two comparison tests are what is left. Okay. So for direct comparison, you just choose the easiest thing you can to compare it to. So with this one, I'm going to compare with 1 over n squared, right? So very similar, it just doesn't have the plus 1. So then you decide which one's bigger. So if I have 1 over n squared, those terms are always going to be greater than the terms in 1 over n squared plus 1, right? Because this denominator will always be a little bit bigger, which means this fraction is always a little bit smaller than 1 over n squared. And I know that the sum of 1 over n squared, my comparison series, from n equals 1 to infinity. That converges because it's a p series with p greater than 1. P is 2. Therefore, I know if a bigger series converges, this is what the direct comparison test says. Oops, focus, baby. Okay, the direct comparison test says if I know something bigger converges, then the smaller one has to converge. So therefore, since our comparison series converged and it was bigger, our given series also converges. So therefore, our answer here is our series converges. Okay, how about the next one? E to the negative n squared. So I'm just going to compare this with something that maybe we already know, e to the negative n. And you might be thinking, I don't already know that, except that you do. Because look, we did it up here, e to the negative n. Okay, so we actually do. We've already worked that one out with the integral test. So you need to figure out which one's bigger. Remember, e to the negative n, that's like 1 over e to the n. And e to the negative n squared is like 1 over e to the n squared. So, when we're talking about fractions, if the denominator is bigger, the fraction is smaller. So since this denominator is bigger, that fraction is smaller. Okay, so first you figure out which way the greater than less than goes. And if you know the bigger series converges, then you know the smaller series converges. So because our comparison series, 1 over e to the n, converges, I'm just going to write C above, converges C above. Therefore, our given series also converges. Okay. The other part of this rule, which wasn't represented here, is if you know a smaller series diverges, then you know the bigger series will also diverge. Okay, and then finally we have our limit comparison. So once again, we're just going to try to pick something simple to compare this to. So if this didn't have a plus 1 on it, wouldn't that just reduce to 1 over n? So that's what I'm going to compare it with. So compare to 1 over n. Okay. So the limit comparison test, a little bit different than direct comparison. To do this, what you're going to do is you are going to take the limit as n goes to infinity of what your series over your comparison series. Okay? And I don't think it matters which one goes on top, but I think we always just kind of do the original one over the comparison. And the rule is it converges if you get a limit, and if the comparison series converges. It diverges if you get a limit and the comparison series diverges. So basically, if this limit exists, then our given series has the same behavior as our comparison series. So let's solve the limit. So the limit as n goes to infinity of n over n squared plus 1, then I'm going to flip and multiply, make that n over 1. So we get the limit as n goes to infinity of n squared over n squared plus 1. And using Bobo button, that goes to 1. So the rule is, yes, we got a limit, which means they have the same convergence behavior. So since we got a limit, and we know that the sum from n equals 1 to infinity of 1 over n diverges. Remember, that's one that really you should have memorized, but it's because it's a p series with p less than or equal to 1. This diverges, therefore, our given series also diverges. So before you know that they have the same behavior, you have to check that this limit equals a number, that it exists, doesn't go to infinity. Okay, so for the next one, let's think about what we should use for our comparison. So once again, if you kind of get rid of the constants, like the 4 and the 1, just boil it all down, you'd have n times the square root of n squared. So it's like n times n. So I'm going to compare with 1 over n squared. Okay, I'm going to do this in a slightly different order. So first I'm going to establish the behavior of the series 1 over n squared. And I know that converges because it's a p series. Okay, with p greater than 1. So my comparison series converges, so that means if this limit exists, the regular given series also converges. So I'm going to take the limit as n goes to infinity of my given series divided by my comparison series. So I'm just going to flip and multiply my comparison series. So I have limit as n goes to infinity of basically 4n squared over n times the square root of n squared plus 1. And when you're trying to do Bobo-Botten here, you can kind of ignore this plus 1. So the bottom, the power on the top obviously is squared. If you're trying to figure out the power on the bottom, the square root of n squared is just n. N times n is n squared. So this is like exponents are the same, even though it's a little more complicated than that. It behaves as if exponents are the same. So that means we divide the coefficients, 4 over 1. We get the limit as 4. So because the limit exists, they have the same comparison behavior, the same convergence behavior. So since the series 1 over n squared converges, our given series also converges. Okay. All right, so that gets you through page 6. We did page 7 already and kind of went over that. So now I want to go to page 8. And this is the last page that I had assigned on Friday. So it says, which of the following series converge? And this is a lot of times how they'll ask convergence questions on the AP test, is questions like this. Well, these type of multiple choice questions where you're picking 1 only, 2 only, 1 and 3, all of them or whatever. Okay, so let's just kind of go one by one and tell whether they converge or diverge. I'm not going to show quite as much work as I did on the previous page. As soon as we figure it out, we'll just write converge or diverge so we can answer the question. Okay, first one is an alternating series. So I'm going to use the alternating series test, which says that, and it's okay if you keep having to look back and see what the tests say. It takes a little bit to get them down. So the alternating series test says that terms need to decrease and the terms need to go to 0. So in this part, do the terms go to 0? Yes, as n goes to infinity. Do the terms decrease? Are the fractions getting smaller as n gets bigger? Yes. So by the alternating series test, this converges. I need to put alternating series. Okay, the next one. That's a geometric series. No, it's not. Whew, almost got tricked there. It looks geometric, but the reason why it's not is because it's multiplied by that 1 over n. So that kind of throws a wrench into it. So we need to pick a test to use. I'm going to use the ratio test. So that means I look at the limit as n goes to infinity of a sub n plus 1 over a sub n, the absolute value of that. So I have 1 over n plus 1 times 3 halves to the n plus 1 divided by 1 over n times 3 halves to the n. So I'm using the ratio test. Let me just write that here. I like the ratio test. So, anytime, especially if like an exponential involved, ratio test is really good. Okay, so the limit as n goes to infinity of, so I'm just going to kind of flip the bottom and multiply and see what I can cancel out. So 1 over n plus 1 times 3 halves to the n times 3 halves to the first. So that's what that is. Okay. And then, let's see. Trying to think what I can. So then I'm going to multiply this by n over 3 halves to the n. So I'm kind of flipping this. So the 1 over n flips. This flips to go to the bottom. Okay, so that allows me to cancel these out. So we have a limit. I'm going to combine it all together. So n goes to infinity. So I have n over n plus 1 times 3 halves. Put the 3 halves up here. Yeah, that's all I have left. Okay, so using Bobo-Botten, each DC, wouldn't that equal 3 halves? divide coefficients. And the rule for the ratio test is that the limit has to be less than 1. This is greater than 1. Therefore, it diverges due to the ratio test. Okay, so that's one you definitely want to check because it's not geometric, so you can't just use a geometric rule. Okay, then the last one, 1 over n, natural log at n from 2 to infinity. So this one, it's not quite like 1 over n. It might be kind of hard to compare with the natural log. So a good thing that pretty much always works, but it's kind of a pain, is the integral test. So that's what I'm going to do. Okay. So for the integral test, the terms have to be positive and decreasing. So starting at n equals 2, these terms will all be positive, and they will definitely be decreasing because the bottom is growing. So they're positive, yes. Decreasing, yes. You have to check those two things before you can use the integral test. So do the integral from 2 to infinity, or 2 to b, as the limit as b goes to infinity, of 1 over x, natural log x, dx. So I'm just changing the n to an x. Okay, you have to use u substitution to solve this. Yay, what great review opportunity. So u is natural log x, du is 1 over x dx, which we'll substitute in there perfectly. So when we substitute that in, the 1 over x dx is here, the natural log x is there. So it would just be 1 over u du. So the integral of that is just natural log absolute value of u, which put the u back in, we get natural log of the natural log of x. Okay, so I'm going to go and put back in the limits and all that. So the limit as b goes to infinity of the natural log of x from 2 to b. So the limit as b goes to infinity of the natural log of b minus the natural log of 2. Wow, so as b goes to infinity, this natural log here on the inside will actually go to infinity, which means this outside natural log will go to infinity. But if you graph it, man, it's going to increase so slowly, but it will keep increasing forever. So since this integral equals infinity and it diverges, that means this series diverges also. So diverges, converges. Our answer is 1 only, A. Okay, next one. So much good practice here with convergence. Okay, so we have 2 over k squared plus 1. Let's see. This is similar to a p-series. P-series are like, 1 over n to the p or 1 over k to the p. So I'm just going to do an easy little comparison here. So I'm going to compare to 1, or let's just say to 2 over k squared. Okay, to 2 over k squared. So I'm just kind of getting rid of that plus 1. So 2 over k squared plus 1 is always less than 2 over k squared. And since I know that 2 over k squared converges by the p-series test, that means this one also converges. So this is by direct comparison. If I know a bigger series converges, then I know the smaller series converges. So this is a p-series. So you kind of have to use the p-series test and the direct comparison test to figure that one out. This one is just geometric with r less than 1. R less than 1, geometric, which means it converges. Okay, easy peasy, as my daughter says. This last one is alternating. So you take out the part that's not alternating, and you see do the terms go to 0? And yes, they do. Terms go to 0, and terms decrease. Yes, the terms have to go to 0, they have to decrease. And if that's the case, then your alternating series converges. So all of them converge. Hold on. Oh, okay, good. Whew, I was like, I don't see my answer. The question is, which of the following series diverge? So none of them diverge. Okay, the last one. Which of the following series converge? So, okay, let's see. This first one, hold on. If we just look at n over n plus 2, those terms are going to 1, not to 0. So this fails the nth term test. So this fails the nth term test. Therefore, it diverges. So that one was easy enough. Oop, here's one that you should have memorized. The 1 over n series diverges because it's the p series of p less than or equal to 1 diverges. So the only one we have left is this kind of weird one with the cosine n pi. But if we think about cosine n pi, and n are whole numbers starting at 1, we'll think about it. What's the cosine of pi? -1. What's the cosine of 2 pi? 1. Cosine of 3 pi? -1. Cosine 4 pi? 1. And you can see they're just going to go back and forth, -1, +1, -1, +1. So really, this cosine of n pi, that's the exact same thing as -1 to like the n plus 1 or whatever. So all this means is that it's alternating. So it's just kind of a disguised way of making an alternating series. And so the alternating series of 1 over n, we know converges. We've done that one several times. Remember, the rule is with it's alternating, your terms just have to go to 0. So the terms in 1 over n go to 0 for sure, and they have to be decreasing, which they are. So converges by the alternating series test. So this one fails the nth term test. The terms don't go to 0. This converges by alternating series. This diverges because the p series with p less than or equal to 1. So which of the following series converge? 2 only. Whew! Got you through the homework. I know that was a long video, but hopefully it was helpful, and you can fast forward the parts maybe that you didn't need help with. So now, if you get caught up on that, I'm going to be posting a worksheet with additional convergence practice, as well as some notes for page 9. So you'll be assigned page 9 in the packet, following the notes video, and also a worksheet. All right, bye-bye.